Hello everyone, welcome to General Physics 1. So in this lecture we'll talk about the first module. So the first module will start with the science of physics and introduction to physics. So in this lecture, in this module, we'll discuss three sections: what is physics, measurements in experiments, and the language of physics. So in section 1, so these are the objectives. First, we'll try to identify the activities and fields that involve the major areas within physics, and then try to describe the processes of the scientific method and describe the role of models and diagrams in physics. So let's start with branches of physics. We can divide physics into 8 different branches. So these are the 8 different branches that we can divide it into. First one is mechanics, thermodynamics, vibration and wave phenomena, optics, electromagnetism, relativity, and quantum mechanics. So mechanics is the subject that deals with motion and its causes and how two objects interact in their motion. An example of this would be falling objects, friction, weight, spinning objects. All of these are examples of mechanics. So next one is thermodynamics. Thermodynamics deals with heat and temperature, is the study of heat and temperature, and it is examples of this would be melting, freezing, processes, and engines and refrigerators. All of these involve thermodynamics. So next is vibration and wave phenomena. So it specifically uses the specific type of repetitive motion. We call that vibrational motion or oscillatory motion. Examples of these would be springs, pendulum, and sound. Next is the study of light, which we call optics. So examples of these are mirrors, lenses, color, and astronomy. Next we have electromagnetism, which deals with electricity, magnetism, and light and their interactions with each other. Examples of these would be electrical charge, circuitry, permanent magnets, and electromagnets. Relativity is the next one, is one that deals with the particles that move at any speed, including very high speeds. So these are mainly examples of these are particle collisions, particle accelerators, and nuclear energy. Quantum mechanics is the behavior of submicroscopic particles, and examples of these would be the atom and its parts. So what is the goal of physics here? So goal of physics here is to use a small number of basic assumptions, basic concepts, equations, and assumptions to describe the physical world. So in simple sense, so what is physics? So physics in simple sense is the study of nature and the natural phenomena. So this is simply the definition of physics. So we basically study the nature and the natural phenomena that occur. Now, physics comes from the Latin word physica, Greek word physica, which means motion. So because initially physics was specifically targeting motion, so the mechanics that we now know of is the original part of physics that started physics. So initially the ideas behind motion of planets, all of that went into astronomy, and motion of bodies, when you talked about Newton, Newton's laws were the basis of motion and physics by itself. So these physics principles can be used to make predictions about a broad range of phenomena. So we can take a prediction and we can use it to explain a broad range of phenomena. So physics discoveries generally often turn out to have unexpected practical applications and generally advances the technology that can turn into new physical discoveries. So an example of these would be the idea behind the semiconductor. So the physics behind semiconductors led to the formation of diodes. Diodes lead to the formation of transistors. Transistors are the essential bloodline of computers. So these are the heart of computers. Without transistors, there's no computers. So this is the idea behind a simple example of thinking about physics by itself. One other one would be to look at physics in terms of, if you consider electromagnetic spectrum, you can have a lot of, so this leads to the understanding of electromagnetic spectrum. For example, if you take from the electromagnetic spectrum X-rays, X-rays can be used to diagnose and identify medical conditions. For example, another example would be to take quantum mechanics. So quantum mechanical principles are the bloodline for lasers. So lasers are now treated as used in medicine. They are also used in many other fields, for example, industry to cut metals, very hard metals. So these are examples of where physics can translate the basic principles into identifiable devices in the physical world. So when you take a simple car generally takes into consideration, if you start with the wheels, you consider mechanics, the spinning of the wheels, start with spinning of the wheels, and the tires that provide enough friction for traction. When you take vibrations and mechanical waves, these are the radio speakers and the shock absorbers that take in the shock when you're going up a bump or when you're going into a hole. Next, you have optics, which are generally going to denote headlights and rear view mirrors. You have electromagnetism, which considers the battery, starter, and headlights. You have thermodynamics, which talks about efficient engines and use of coolants, how to keep engines efficient. So this is the simple way in which you can think about physics in the entire system of a car. So next, let's talk about the scientific method. So there is no single procedure in general that scientists follow in their work. However, we use certain common steps in all good scientific investigations. So these steps in general are called as the scientific method. So what is the first step? The first step is to make observations and collect data that leads to a question. Second, once you have that question, formulate and objectively test hypotheses by experiments. Next, once you have conduct the experiment, interpret the results and revise the hypothesis if there is a necessity to revise it. And then finally, state conclusions in the form that can be evaluated by others. Unless your results can be reproduced by the other person, then there is no point in conducting an experiment. If your hypothesis works, it means that somebody has to be able to reproduce your own result. So to reproduce that, we use models. So physics uses models to basically describe phenomena. So what is a model? A model is basically a pattern or a plan or a representation or a description designed to show the structure or workings of an object, system, or a concept. So for example, if you take a set of particles or interacting components considered to be a distinct physical entity for the purpose of study, we call that a particular system. So whenever we talk about a system, we're talking about a set of particles or interacting components which we consider to be the main purpose of study by distinguishing it as a distinct physical entity. Now, what are hypotheses? So models help scientists develop hypotheses, and a hypothesis is basically an explanation that is based on prior scientific research or observations that can be tested. Remember that a hypothesis cannot be anything. It's not a guess, it's a scientific guess. So what does the word scientific guess relate to there is that it basically explains something that is based on prior scientific research or observations, and you can always be able to test it. Now, the process of simplifying and modeling a situation can help you determine the relevant variables and identify a hypothesis for testing. So this is really important in the scientific method. So let's take a simple example of a hypothesis. So how Galileo modeled the behavior of falling objects in order to develop a hypothesis of how objects fall. Now, the idea was that, let's say, if you had two bricks of two different masses, so one is a really small one is a really large one. The idea behind the experiment here states that if the smaller object falls with slowly and the larger object falls fastly, then if you connect the two objects, will they slow down or will they speed up? What would be the idea here? Now, either one has to slow down because the smaller object will try to slow down the larger object, or the part will speed up because both of them are giving an additional mass. So this is where the point comes in, where he said that if both objects even had different masses, they do fall at the same rate. So if the heavier objects fell faster than the slower ones, would two bricks of different masses tied together, will they fall slower or faster? than the heavy brick alone. So then because of this contradiction, so what Galilei hypothesized is that instead all the objects generally fall at the same rate as in, because you cannot have two different results for the same question. So which basically means that if they are even tied up, it doesn't mean that if they are they fall slowly or faster, they cannot do both of them at the same time. So which means that that's when the idea contradicted that. So both of them will fall at the same rate. Next, let's talk about controlled experiments. So a hypothesis in general must be first tested in a controlled environment or a controlled experiment. So what is a controlled experiment is where we only have one factor at a time by using a comparison of a control group with the experimental group. So control group is what differentiates the experimental group. For example, if you take Galileo's experiment, he would take bricks of different masses, and if you would let them fall down. And here, what would be a controlled experiment was to take objects of the same mass as well as the objects of different mass and try to see if there is any differentiation at the rate at which they fall down to the earth. So that is the topic, that is section 1. Next, let's go to section 2, where we talk about measurements in experiments. So in this section, we'll list the basic SI units and the quantities they describe. Second, we'll try to convert measurements into scientific notation. Third, we'll try to distinguish between accuracy and precision. Finally, we'll use significant figures in measurements and calculations. So if you recognize this word significant figures, you might have come across this in chemistry already. If you haven't come across, we'll be discussing them in this lecture as well. So let's talk about numbers as measurements. So in the SI, so SI here refers to System of International Systeme Internationale, which is the French word that we use for international system of units. So this is the standardized system that we use in worldwide, that make sure that all scientific experiments have the same base units. So this starts with the measurement system starts for science, but there are 7 base units. So each base unit describes a single dimension, which is such as length, mass, or time. So for example, the units of length, mass, and time are meter for length, kilogram for mass, and second for time respectively. So next we have derived units. Derived units are formed by combining the 7 base units with multiplication or division. For example, kilogram square, or for example, we can write it as kilogram square or kilogram meter per second square, like that. So for example, if you take examples of speed, speed is recorded in the units of meter per second, where we have 2 fundamental units, meter and second. So now let's delve into first what is a physical quantity. So we define physical quantity if it shows 2 particular characteristics. One is accuracy of measurement, and second is the adequacy of expression. So if a quantity can satisfy these 2 conditions, then we call that a physical quantity. What is the accuracy of measurement here? So accuracy of measurement basically says that you should be able to measure it accurately with a particular any device. So you should be able to measure a particular quantity accurately. For example, if you say affection cannot be a fundamental quantity or a physical quantity because you cannot measure it accurately, or you cannot express it in terms of adequate expressions. So in terms of a mathematical expression. So for example, mass, I can measure the mass using any measuring devices, and I can express it in the form of an equation as well. So these are examples of physical quantity. So a physical quantity is one that has to have both accuracy of measurement and adequacy of expression. Adequacy of your expression refers to the idea that any physical quantity you should be able to measure it. You should be able to write it in the form of a mathematical expression. So that is the idea behind the physical quantity. So we divide physical quantities. So we divide physical quantities into three types. So first one are fundamental quantities. Second are derived quantities. And fourth are supplemental quantities or supplementary quantities. So let's start with fundamental quantities. So what are fundamental quantities? So fundamental quantities are the base quantities. So these are the base quantities by which all quantities are derived. So these are the base quantities from which every other quantity can be derived. So these cannot be expressed in the form of other quantities. So each of them are unique and cannot be expressed as a combination of other quantities. So in total there are 7 of these quantities. So the first is mass, second is length, third is time, fourth is thermodynamic temperature, so the other name for thermodynamic temperature is absolute temperature, fifth is current strength, fifth is electric charge, sixth is luminous intensity, seventh is the amount of substance. Each of them have their own units, so the SI units or the fundamental units. So mass, the unit is meter, mass, the unit is kilogram, kg, length, the unit is meter, em, time, the unit is second, s, thermodynamic temperature, the unit is Kelvin, uppercase K, charge, the unit is Coulomb, uppercase C, luminous intensity, the unit is candela, CD, amount of substance, the unit is mole, MOL. So these are the fundamental quantities and their units. So every other quantity can be expressed as a multiplication or division of one or more of these quantities. So let's talk about the next type of quantity, which are derived quantities. So as the name itself says, these are quantities derived from the combination of fundamental quantities. So these are the quantities that derive from the combination of fundamental quantities. So an example of this would be, for example, say this velocity. So velocity v is displacement by time. So displacement is length. So length is meter over time is second. So the unit will be meter per. So the unit is meter per second, or we can also write it as meter second inverse. So notice that here you have two fundamental quantities, meter and second. So two fundamental units that are combining to give you a unit. We call it the derived unit. So we call it the derived unit. So this is the idea behind derived quantities. So every quantity other than the fundamental quantities are derived quantities. Now, what are the standards that we use? For example, whenever we define the unit meter, we have to know what is the measurement that is taken as an actual value to understand what is the actual standard represented by the unit. So when you take the unit meter, so the original standard that was taken was 1 by 10 million distance from equator to that of the North Pole. That was the original standard. But the current standard that is used is the distance traveled by light in vacuum in 3.3356405 times 10 to the power negative 9 second. So this is the distance that is traveled in this amount of time is now the actual unit for meter. The second one is kilogram. The original standard was the mass of 0.001 cubic meters of water. The current standard is the mass of a specific platinum iridium alloy cylinder until 2018, and then the standard was changed to a combination of fundamental quantities. The combination of constants. So at present the standard is a combination of constants that are used to derive the unit 1 kilogram. So next one is second. Second was originally 0.000011574 average solar days. Now it is used by using radioactivity, which is 9,192,631,770 times the period of radio wave emitted from a cesium-133 atom. So that is now considered as the unit for time. Next, let's talk about prefixes. So what are prefixes? Prefixes are an easier way of shortening symbols of powers of 10. So we are basically symbolizing certain powers of 10. And so in this table it shows you common prefixes that are generally used. So let me write a small table so that you understand it better. So we are going to look at it from 10. So from 0 if you go up and if you go down. So let's look at larger prefixes or macrocosms. So macrocosms are when you start with 10. 10 is deca. 10 power 10 square is hecto. 10 cube is kilo. So from 3 you go into multiples of 3. 10 power 6 is mega. 10 power 9 is giga. 10 power 12 is exa. 10 power 15 is tera. 10 power 12 is tera. After that we have 10 power 15 is peta, and 10 power 18 is exa. So deca is denoted by D. So the 10 power 10 is denoted by dA. Hecta is denoted by H. You have kilo denoted by small k, mega denoted by uppercase M, giga by uppercase G, tera denoted by uppercase T, peta denoted by uppercase P, exa denoted by uppercase E. So these are the symbols that we use and the prefixes. Let's go into the microcosms, which are 10 power negative 1, which becomes deci denoted by D, 10 power negative 2 denoted by centi, C, small case c. 10 power negative 3 is milli denoted by small case m. Again we go into multiples of 3, so you have 10 power negative 6 which goes into micro denoted by mu. 10 power negative 9 becomes nano denoted by small n. 10 power negative 12 denoted by pico small case p. 10 power negative 15 denoted by femto smaller case f. So 10 power negative 18 denoted by atto denoted by smaller case e. So these are the prefixes and their symbols that we use. For example, if you have a unit 3 times 10 to the power negative 6 meter, it can also be denoted by converting 10 power negative 6 into micro and writing it as 3 micrometer. So remember here that you cannot combine unit and you cannot have 2 or more prefixes at the same time. For example, if you have 3 into 10 power negative 3 centimeter, you cannot write it as 3 microcentimeter. So this is wrong. First, convert it into SI units, which is 3 into 10 power negative 3. Centimeter can be written as 10 power negative 2 meter. And then writing it into the SI unit, which is 3 into 10 to the power negative 5 meter. And then try to convert this into the original unit. So here, if you want to convert this, I can divide 10 on both sides. So that gives you 0.3 micrometer. So this is how this unit can be written as. You cannot have more than one prefix at the same time. So this is the idea behind prefixes and suffixes. Next, let's talk about dimensions and units. So measurement of physical quantities must be expressed that match the dimensions of that quantity. So in order to have the correct dimension, so we have to use measurements that used in calculation should have also the same units. So for example, here they are giving us that the typical bacterium has a mass of 2.0 femtograms. Express this measurement in terms of grams and kilograms. So first, we have 2.0 femtograms. So we know that femto refers to 10 power negative 15. So we can write it as 2.0 into 10 power negative 15 grams. Now, I know the conversion in grams, but I do not know how to convert it into kilograms. How do you convert it into kilograms? So when you take the question here, so it says that 2.0. So what is 1 gram? So what is 1 kilogram? So we know that 1 kilogram is 10 to the power 3 grams. So if I want to convert this into kilograms, so what should I do here? Is basically remember that here 2.0 into 10 power negative 15 grams should be something dash kilograms. So for this to be done, so the easiest way to write down this on the gram side, so 2.0 into 10 to the power negative 15 grams is x kilograms. So let me write it here as x kilograms. What you can do now is cross multiply the values. So cross multiply the values, and once you cross multiply, you get 1 kilogram times 2.0 into 10 to the power negative 15 grams is equal to x kilograms into, so we do not need to write the units here, so we just need the value of x here. So x times 10 to the power 3. So now we have to find x here. So x becomes 2.0 into 10 to the power negative 15 by 10 to the power 3. So you know the rules of exponents here. When you divide, you subtract. So 2.0 into 10 to the power negative 15. So this is a power m over a power n. So which becomes a power m minus n. M is negative 15 and n is 3. So negative 15, negative 3. So it becomes 2.0 into 10 power negative 18 grams. So x value here, not grams, sorry. So this is the x value is 2.0 into 10 power 18 negative 18 grams. So take this statement specifically. So we only want this statement here. We do not need anything else. So what does that statement say here? So x kilograms is 2.0 into 10 power negative 15 grams. So what is that x value here? So the x value is 2.0 into 10 power negative 18 kilograms becomes 2.0 into 10 power negative 15 grams. So this is how you can convert from one prefix to other prefixes. So always use the main one as the justifying one, and cross multiply the values by arranging them in an order. And when you cross multiply the values, whatever you are left with as the value, So what the unknown value, write it as x, and that x value becomes your answer. So this is how you can convert from one prefix to another prefix system. Next, let's talk about accuracy and precision. So accuracy here is a description of how close a measurement is to the correct or accepted value, and precision is the degree of exactness of a measurement. So even though they look the same, it doesn't actually mean the same. Accuracy specifically refers to how close is the measurement to the actual value of the original quantity. Precision basically refers to how close are the values. For example, precision here is a process of repetition. Accuracy here refers to how closeness. So these are two separate things. Even though they nearly mean the same, they are two separate things which can be described as, so whenever you have a numeric measure of confidence in a measurement or result, it's called as an uncertainty. And uncertainty, lower the uncertainty indicates that the greater the confidence. So what is the idea behind accuracy and precision? So let's take a simple example. So let's say I have a diagram here that shows you an archer's ring and you're trying to shoot arrows. Now notice here that this here, the center here, is your target. Now in this diagram, you're hitting your arrow nearly close to the target, but you're really far away from the target, but your arrows are hitting close to one another. So your arrows here are really close to one another. This is an example of a measurement which is really precise but not accurate. So this is an example of a measurement that is precise but it's not accurate. Let's take another example of a measurement. So this is an example where you have scattered values. So you notice that this is scattered, but in terms of the distance from here, from the last measurement, this is actually closer to the target here. So these four are examples of measurement which are accurate but not precise. So there are easier meanings to understand based on what we have. So you can make different assumptions about the measuring instrument based on the way in which your measurements are scattered throughout. This is just an analogy of what is precise and what is accurate. Let's take a realistic understanding of how precise and accuracy, precision and accuracy work. So let's say I'm trying to measure. So let's say I'm trying to measure a particular length of a diameter of a rod. Then I'll take, let's say for example, I'm taking a screw gauge. So the device I'm using is a screw gauge. And this screw gauge, I'm trying to see whether it is accurate and precise. So how would you measure that? For example, let me draw the first trial of measurements with the first line. So for example, let's say if my measurements are scattered every trial, and all of my measurements here, every time I measure with this particular screw gauge 1, so all of these measurements are really close to the actual value and they generally form. So whenever, what you can do now is try to connect lines from one to the other. So my line here is really close to the original line. So which means this is an example of accurate but not so precise. Let's say I have another screw gauge 2. So this is the first red one is the screw gauge 1 and second one is the screw gauge 2. Screw gauge 2 I'm getting measurements, but all of those measurements are concentrated on a particular group of values and they're really close together. So this is an example of accurate and precise. I'm sorry. So this is an example of accurate and precise. So let's take this in the second set of values here. In the second set of values, if this is the original values, so if this is the original value or the actual value of the measurement. And this is the line that I'm getting using screw gauge 2. This is an example of precise but not accurate. Next, I have another line. Let me say, for example, let me draw with some other color. So let's say I'm getting one value here, one value here, one value here, one value here, and one value here. Let me connect the dots here for these two. So the green here represents the structure, the measuring device that is neither precise nor accurate. So this is an example of a device that is neither precise nor accurate. So this is how you generally see the idea behind precision and accuracy in terms of the actual device. So when the measurements are really close but not accurate, so there is a standardization that we generally use, which generally says that this is not a measuring device error, so this is a device error. So this is a device error. And when you have neither precise nor accurate measurements, this is an example where you might end up getting what we call human errors or experimental errors. So this is where the environmental conditions might not be accurate for you to use that device, or device errors. So that might be the person where. So device errors can be corrected by adjusting a value, by putting an adjustment value. But human errors should be tried to be minimized. So you can try to minimize it, but they will always exist anyway. So this is the idea behind accuracy and precision. Next, let's go to the next topic, which is significant figures. So it is important when we measure things, we have to record the precision of your measurement, so that whenever you have other people can understand and interpret your results. So one of the most common conventions used in science to indicate precision is called as significant figures. So these are basically digits in a measurement that are known with a certainty plus the first digit that is uncertain. So whenever you see, for example, let's take an example of this particular pencil measurement. So let's say I'm trying to measure this length of this pencil on a scale, and when I look closer, notice that the sure digit that I know here is 8. So I surely know that is 8, but it extends a little bit outside. So the first digit that we have here is 8, but the second part is this extension. I can say 8.5, but I'm not sure. So when I write 8.5, I'm basically saying that the first digit is sure, but the second digit is uncertain. So this is the idea behind precision. So what are the rules when we determine the significant zeros? So what the first rule is that whenever you have zeros between other non-zero digits, those are considered to be significant. So in this particular measurement, where there are two significant figures, but here we can consider, for example, 50.3 here. The zero here is between two non-zero numbers, so it has three significant figures. The second rule, the second rule here is that zeros in front of non-zero digits are non-significant. For example, 0.892, here this 0 is not considered significant because it is before the non-zero digit. So this is considered to be the significant, and this is considered to be not significant. So this here, 0.892 has three significant figures, and 0.0008 millisecond has only one significant figure. Next, the second one is that zeros at the end of the number, also to the right of the decimal, are significant. So the end of the number as well as the right. So when you have the end of the number here, there are two zeros. So here it has a total of 4 significant figures. So here there are multiple zeros, 6 zeros. So we consider there to be 7 significant figures. Next, so zeros at the end of a number but to the left of a decimal are significant if they have been measured or are the first estimated digit. Otherwise, they are not significant. So for example, in this book, we'll be treating them as not significant. So some books can use it as significant, but in this book specifically, in the textbook that we use, we are going to consider them to be significant. For example, 1000 meters can have 1 to 4 significant figures, provided on the precision of the measurement. So if the measurement is written as 1000.0, so whenever we write, for example, 1000 point, this considered to be having 4 significant figures. But when you write just 1000, the chances are it can have an uncertainty of 1 to 4 significant figures. The reason 1 to 4 is because there's only one certain figure, the other 3 are not certain, so that's the reason why we considered them to be not significant. Next, what happens when you add or subtract two numbers? So when you add or subtract, given that the addition and subtraction take place in columns, so when you round up the value, we are going to take the one that has the least number of decimals. So the significant figures, so the answer should have the least number of decimal positions. So the number that has the least number of decimals. For example, 97.3 and 5.85, when you add up, you get 103.15. But notice that here, it should have the same number of decimal places as that of the one that has the least number of decimal places. Here 97.3 is the one that has one decimal place, so the final answer should also have one decimal place. What happens when you multiply or divide? The final answer here should have the same number of significant figures as the measurement having the smallest number of significant figures. So we are considering two numbers. When you multiply two numbers, the final answer should always contain the same number of significant figures as that of the least number of significant figure number. For example, here both of these have 3 and 3, so which means that the final answer should also have 3 significant figures. So next one is rounding off. So rounding off is where when you have, how do you round off 658.05 to 658? So it depends on 5 here exactly. If the number that you are rounding off is 5, sorry, if it is greater than 5, we add +1 to the preceding number. If it is less than 5, we add 0 to the preceding number. Now, if it is equal to 5, we get two cases. Depending on if the preceding number is even, we add +0. If it is odd, we add +1. So how do you round off? For example, let's say I have a number here where I have 631.225 and I have to round this off to 4 significant figures. So how do you round off? Take the last digit, so 5. This is 5, so which means we are going to check the rule of the preceding number. Preceding number is even, so we are going to add +0 and remove that number. So we have 631.22. Next, we have to take the next number 2. So this number is less than 5, so we are going to add 0 to the preceding number and cancel this out. So we have 631.2. So this is your final answer that has 4 significant figures. So this is how you do rounding off. Say for example, I have 630.333 and I have to round this off. So I have to round this off to, let's say for example, 3 significant figures. How would you round this off to 3 significant figures? First take the last number. So the last number is 3. Let me write it as 383. So the last number here is less than 5, so we add +0. Next again 3, which is less than 5, we add +0 to the preceding number. Next we have 8 here. 8 is a number that is greater than 5, so to the preceding number we add +1. So the final answer becomes 631. So this is the final answer with 3 significant figures. So this is how you round off of certain values. So with that we end the topic on measurements in experiments. Next, let's talk about the next section, the language of physics. So in this section, so these are the objectives. First, we'll try to interpret data in tables and graphs and recognize the equations that summarize data. We'll try to distinguish between conventions for abbreviating units and quantities. And third, we'll try to use dimensional analysis to check the validity of equations. Finally, perform order of magnitude calculations. So first we have mathematics and physics. So tables, graphs, and equations. These are all graphical representations that can make data easier to understand. So for example, let's consider the Galileo's experiment where Galileo tried to test his hypothesis where the objects try to fall at the same rate in the absence of air resistance. In this experiment, we have a table tennis ball and a golf ball dropped in vacuum. So we are recording the results as a set of numbers corresponding to the times of fall and the distance of each ball falls. A convenient way to organize this is to form a table, and this is how the table would look like. So what will happen here? We are basically taking a golf ball. So we are taking the distance of the golf ball and the distance of the table tennis ball by their centimeters and the total time taken. So we are going to record for each distance how much is the time it takes. So notice that here for 2.20 meters for both of them, they're taking the same time. Again, 8.67, they're taking the same time. Next value, again, they're taking the same time. Now, once from these results, when you notice that the values that we are calculating, the distances are really close to each other, we notice that these are a clear trend here can be seen in the data. So the more time that passes after each ball is dropped, the farther the ball will fall. So this is the idea behind. So from the table, we are basically interpreting the idea of what we need as the answer. So when you draw the same graph, you end up getting a graph that is much more a relationship of a linear relationship that shows the idea here. Next, physics equations. So physicists use equations to describe measured and predicted relationships between physical quantities. So when you have variables, so variables in this lecture can be either bold-faced or italicized. So units in general are abbreviated with the regular letters, sometimes generally using Roman letters. So two tools here are used for evaluating physics equations. One of them is dimensional analysis and the second one is order of magnitude estimates. So whenever we have equation from a drop ball experiment, so we can calculate this experimental value as change of position in meter is 4.9 times time in seconds square. So which can be written as delta y equals 4.9 times delta t square. So here we are using delta. Delta is a symbol that can represent change in, and when we write delta y, we are basically representing that there is a vertical change in the ball's position, and when we are representing delta t, there is a change in the time. So this equation here allows you to reproduce the graph and can be used to also make predictions about the change in position for any given amount of time. So this is the idea behind the language of physics. So physics uses the language of mathematics to represent data clearly, and this is one of the reasons where mathematics plays a big role in the ideas of physics. So with that, we end the first module on the science of physics. I will see you again in the next lecture.